Alright, and welcome to part 4, hopefully the final part of our uh, thermal energy notes. Alright, first, just to recap what we did on the last problem, there's one problem here. This one is joules per kilogram times degrees Celsius. So first of all, we need to change this to kilograms, and we would do that by dividing by 1,000, which would make that 0.032 kilograms. Wrinkle there. And so basically you should have got about 300.8, give or take a little bit, joules. Now, if you're not sig digs and stuff, you could worry about that, but we won't worry about that right now. Just make sure you got the right answer. If you got 300,800, then that was just because you had to divide by 1,000 there. My bad. Okay, but that's how you would do the Q problems, and yes, you'll get a chance to practice those some more on other things. Next, we want to talk about how to transfer energy from one object to another, because that's what heat, we said, is all about, is when heat or thermal energy is transferred from one object to another, from hotter to colder. There's three main ways it can do that. Number one is conduction. No, that is not what the engineer does on the train. Well, that is conducting of a sort, but not conduction that we're talking about. Conduction is when something touches something else and it transfers the heat by touch. The key thing is a direct contact as they're doing that. Now, that occurs in all three phases, but it happens the fastest in solids. All right, they're number one because the atoms are crammed close together, so it's easy to pass the heat from one molecule to the next, to the next, to the next, and so on. And so solids tend to be the best. Liquids would be next, and the worst would be gases because they are far apart, bouncing all over the place, and the odds of them hitting each other are not very good, so they don't pass very much heat by conduction. Okay. Now the second type is convection. All right. Now for convection is when heat is transferred in a fluid. All right, so we need to do a quick definition of fluid. If someone comes in contact with bodily fluids, we know that means liquids, right? But we won't worry about what kind. But yeah, it usually means liquid. But in physics, the word fluid is a word that just means anything that flows. So if you can go with a flow, then you're a fluid. No, okay. But seriously, a fluid is anything that can flow. Now obviously solids cannot flow. They have a shape, they stay in that shape. However, liquids can flow, and so can gases. They can both move, and therefore they can flow. So really we're talking about this convection only occurs in gases and liquids. Okay, it does not occur in solids. And because what happens in convection is the actual liquid, like water in a boiling pan, heats up and it moves. Okay, because as it heats up, say this is the molecules in a liquid. It could also be air in the atmosphere. If it heats up, they get farther apart, and as they get farther apart, they become less dense, so they tend to rise. Okay. Now, as they rise and they spread out farther, they start to cool off, so then they start getting closer back together again, and they start sinking. And so they make kind of this circle. This is called a convection current. Okay. And so when a fluid heats up, which makes it less dense and causes it to rise, then that is called convection. Like I said, it can be a liquid, as in a boiling cup of water or a pot of water, or it can be air, and that's what causes wind, basically. As air rises up here, then air rushes in to take its place, and the air comes down here and just keeps the cycle, this convection current. If we're down here on the surface, we feel that convection current as wind. Anyhow, that's supposed to be a person, believe it or not. Okay, but so that would be like the water. If you see it boiling, you see it rising, and it goes back down, up and down, and makes that little circle inside of there. That is convection. Okay, and it's only going to happen in either a liquid or a solid. Okay. And then last but not least is radiation. Okay, if you were sitting at the campfire, here's the campfire, and you're warming yourself here, Got your hands going. That feels nice on your hands. Yeah, yeah. Okay. All right. And that's good for your hands. Whoops, no knees there. I don't know what happened to your knees, but anyhow. Okay, there we go. All right, this side of your body gets hot. Why? Because it radiates through space, or air in this case. It can be through space. The sunlight goes through outer space, okay, and it hits you. And this whole side of your body is heating up. Unfortunately, this side over here is not getting any, and it can, if it's cold outside, it can be pretty freezing over there. So you're warm on this side because the radiation from here is hitting you, but this side is very, very cold. So radiation is when heat energy radiates through air or space and hits somebody. Okay. Now, generally, when radiation hits a solid or liquid, which is what our body is mostly out of, solid and liquids, it is going to absorb it, and therefore it gets hotter. Gases, on the other hand, let most of the radiation through, and that's why the sunlight comes through the atmosphere with most of the heat or thermal energy intact, and release that when it hits us or buildings or our car seats or whatever else it may hit when it gets there. And these are electromagnetic waves or electromagnetic radiation, and it radiates. Now, in this picture we have all three. We have conduction, where you're touching the handle. That's why a lot of pots are going to have plastic or something that doesn't conduct heat very well, because you're touching it and it's touching the metal. If you have a metal handle, like a cast iron skillet, then the heat goes from here into there and right into your hand. Okay, so conduction is where you touch something. Convection is when a fluid, a liquid or a gas, move and make a convection current usually. Radiation is where it travels through space until it hits something, or air until it hits something. Okay, and those are basically the three kind of ways that you can have heat traveling. All right, now the next part sounds kind of obvious, but basically the bigger temperature difference there is, the faster heat will flow. For example, if I have a cup of coffee, I just like that. Not that I like coffee, but I can draw a coffee cup halfway decently. Okay. When I first boil it, it's very, very hot. And so there's going to be a high heat flow, a lot of heat flow going into the ground. After about 20 minutes, the same cup of coffee is there. Okay. It's still hotter than the air around it, but now there's just going to be a small amount of heat flow because there's not a big temperature difference between the cup and the air around it. Okay, so basically a hot cup of coffee is losing a lot more heat and will lose the heat much faster than a cooler cup of coffee, because there's a bigger difference between the temperature of these. Now, if you think of that in terms of your body, it's kind of fairly obvious. If it's 70 degrees outside, you go outside, you're losing some heat, but not that much. If you go outside and it's 0 degrees, you're going to lose heat really, really fast, because there's a big temperature difference between your body, which is 98.6, and the outside, which is 0. So it's going to flow much faster. So the bigger the difference, the faster the heat will flow. Now, the other thing that affects how much heat flows, besides the temperature difference between the two objects, is the type of material that it's flowing through. All right, this is kind of the science of materials we talk about. And we have invented lots of materials to help us either increase the heat flow or to decrease it. The type of material that affect it would be, number one, the type of material. Okay, what's it made out of? That makes sense. Okay, say you have a plastic cup, or say you have like this Yeti metal cup. Okay, that's going to affect the rate of heat flow and so forth that's going to have through it, either into or out of, depending if you have a hot drink or a cold drink. All right, the first thing is the K value. The K value, and don't ask me once again, why is it K? K value is just the thermal conductivity. That's not very good, but you get the idea. Thermal conductivity, which just means how well does it conduct thermal energy. If something has a high K value, that means it is a really good conductor of heat. And metals, would we say, would be an example of this. They're extremely good conductors of heat. Okay. If you have a low K value, things like air, for example, a lot of glasses just have air trapped between the walls, and that helps decrease the rate of flow because it is not a very good conductor. All right. If you think about a Yeti cup, not only, even though it's made out of metal, the heat has to travel from the metal. then go through the airspace in between, and not only is the airspace, but they have sucked most of the air molecules out, so it's a partial vacuum. There's very few air molecules in between the two walls to transfer the heat in. And even if there are air molecules, they don't transfer it very good, and so that's why it keeps your drinks so cold. All right, and so that's the first thing. All right. Then the next thing is the surface area. Okay. Basically, you're going to lose heat from the surface because that's where the interface between cold and hot are. So basically, the bigger the surface area, all right, then the faster you are going to lose heat. Okay. So there's going to be a lot more heat flow if there's more surface area. And the last thing is the thickness of the surface. All right. And so basically, generally speaking, the thicker the surface is, it's going to take longer for the heat to travel through it. If you have a thin surface, then the heat's going to travel through it in a shorter amount of time, so you're going to have a bigger heat flow. Okay. So it turns out if you were an engineer trying to figure out how much heat is going through it, there's a formula for that. It is the K value times A, or the area, which would be the surface area, times the temperature difference between the two things. Okay, let's say temperature 1 and temperature 2, the cool object and the warm object, like the air and the coffee in the cup, and then divided by the distance. Okay, because the thicker the object, in this case the distance means how thick the substance is. Okay, so this would be how thick it is. So the thicker the substance, the slower the heat flow. The smaller this number, then the faster the heat flow. These ones on top, the bigger the temperature difference, the bigger the surface area, the bigger the K value, then the faster the heat flows. We're not going to really calculate a lot of those, but I just want you to know that general principle, how that works. Now, if we have time, I'll come back and work the problem that's in your thing here, but I'd like to talk about the last part real quick. Is heat flow a good thing or a bad thing? Well, it just depends. So we want to control it. Sometimes we want heat to flow, so that's a good thing. Okay, like a pan, for example. You want the heat to flow through it, so it heats your food up. Other things, like the insulation in your house, you don't want heat to flow out of your house in the wintertime. You want to keep all the heat in. Or in the summertime, you want to keep the heat out as much as you can. So basically, we have conductors, which are things that allow the heat to flow well. Okay. And so if we want heat to flow, then we want to use conductors. Obviously, if we do not want it to flow, then we're going to use insulators, because insulators are things that resist the heat flow. They do not let the heat flow through them very good. And just like conductors have a K value, insulators have an R value. And the R value stands for thermal resistance. There's where the R comes from. In other words, how much does it resist the flow? So the higher the R value, the more it resists the flow of heat, and therefore it is a good insulator. In fact, insulation, when you put it in your walls, based on how thick it is and stuff, has a value like a R19 or R20 or whatever, and that tells you how good of an insulator it is. The bigger the number, the better the insulator. Okay, now the rate of heat flow. Look at the example. First of all, it says the K value. The K value is, thermal conductivity is 0.27 watts per meter per degree Celsius. Okay, times the surface area. Well, in this case, it's a window, so it's 1.2 meters, the width, times the height, which is 1.8 meters. So that's going to give you the area. All right, the change in temperatures between inside and outside, okay, is going to be 25 degrees because you're going from -4 on the outside to 21 on the inside. That's a change of 25 degrees. Okay, and then the last thing, divide by the thickness of the window, which is 6.2 millimeters. Now, to finish this, you would have to either convert millimeters to meters or meters to millimeters so that they would cancel out. Anyhow, if you do that and email me the answer, I will talk to you about extra credit. But that's it for all the thermal energy. Thank you.